Thank you, Michelle, for starting recording. We'll start with Lynn, then we'll continue with Peter after questions for Lynn. Again, short, quick questions can go to Zoom chat, but if you have technical question, please type it to Slack channel. And after Peter, we'll have a short break, and then we will reconvene in Gather Town. Or did I get it backwards? No, we go to Gather Town, then we have a little break and reconvene at 11. And then we have a few more slides from Lynn. Then we'll have contributed slides. We have about 8, I think. And then we'll end up with open discussion. So Lynn, it's all yours.
Thank you. Okay, so this first session today, we're talking about metrics. And in particular, that worked properly, yeah, good. We're talking about, I want to go through the high-level survey strategy evaluation metrics that we have taken. These are sort of the science level metrics that we have that we are taking to use as at least part of the basis of when we're comparing our different simulations. So there are more metrics than these. There are a lot of metrics. But these are sort of the big picture of core science metrics. So they include the Srd metrics, the things like the number of galaxies to sort of represent the galaxy collaboration, cosmology, and this primarily relates to disk, number of stars, the number of the completeness of solar system objects. And we have a few metrics for transient and variable detection. And so these scale with different survey strategy changes. So some are simple, they just scale with the amount of area, whereas more of them are more complex. They depend on the cadence plus the footprint or the filter distribution, for example. Now, we also have a lot of basic metrics like what is the air mass distribution, what is this seeing distribution, the individual image depth. So these are all out there and measured as well, but what we really want to measure is the science return, so that's what we're looking at here. So I will go through these in these groups. So first we have the Srd metrics. So the Srd metrics that we're pulling out for the radar plot, which is not a comprehensive measurement of all of the different science cases, but it does help give you sort of an overview. And we just don't have time here to go through everything. So the science metrics include the what we call FOMV. So this is a measure of how many visits per pointing, but it also has folded in there the area covered and what is the uniformity of coverage over that area. So this says, what is the, if we use the median FOMV, it's saying what is the median number of visits per pointing over the 18,000 square degrees that gets the most visits. So this is a way to measure a quantity that is directly spelled out in the science requirements document. And this is a pretty important one. And it also it comes down to being pretty basic. It's telling you just how many visits did we get over a large area that is 18,000 square degrees.
Lynn, there was a quick question on chat. What does cosmology mean as a metric in your slide?
Okay, perhaps that was too vague. That's coming up next, and it'll be more obvious when we get to what those metrics include. It's just that's the area, the science area that it's representing. So then we have, in the Srd, there's a requirement on what the proper motion is, the proper motion errors are. So here we look at what is the median proper motion error at a couple of magnitudes. And then we have the parallax error. This is sort of driving towards visits with a wide seasonal baseline. And basically all of these Srd metrics are very dependent on the number of visits per pointing. If you have less than 18,000 square degrees, they will all start to crash out pretty quickly. But once you have 18,000 square degrees, At that point, it's just number of visits per pointing within that 18,000 square degrees. So that's how they scale. The plots for these metrics look like up here. I don't know if you can see my cursor or not, but we have this is the FOMV metric. So you can see this is the number of visits over a certain amount of area is that black line. And these blue lines tell you, marks 18,000 square degrees, that red line. The blue line shows you, okay, in this simulation, there was just over 800 visits, median visits per day, or the minimum there. That's, the blue line is the minimum, and then we also measured what the median over that area was. This plot on the bottom left is the proper motion errors across the sky, and then on the right is the parallax errors across the sky. So when we're comparing against different multiple simulations, of course, we can't take these plots and compare the plots quite so easily. So what we do is just take the median value of that proper motion error, the median value of the parallax error, and then basically where these lines intersect for the FOMV. So the number of galaxies, we have a galaxy luminosity function, and for each pointing, we can calculate the co-added extragalactic dust extincted M5 depth, and just say how many galaxies can we detect. So we find, looking at the different simulations, that this primarily scales with the area that we're covering. It does depend on the filter distribution. Better filters are better. And it depends a little bit on the footprint location and a little bit on the number of visits. But because of the way the luminosity function works, the area is the most important. So you can see an example of sort of a baseline traditional survey footprint on the left. And this is the number of galaxy counts per point on the sky. And on the right is the number of galaxy counts per point on the sky for a different simulation where we had a different footprint. You can guess which one of these might have had more galaxies. The one on the right. So cosmology, what is cosmology? So for a lot of the desk metrics, cosmology here, I suppose it's not really limited to desk, but in practice, desk has included, been the source of all of our cosmology-oriented metrics so far. The idea here is that in order to do extragalactic science, it's better to define a particular footprint which has low dust extinction to avoid errors coming from photometry corrections from dust extinction that has a minimum co-added dust extincted depth in I-band, and it has visits in all 6 filters. So then that defines a subset of the pointings that are within the survey. On the top right, you see what that footprint would look like when you just look at the traditional survey strategy. So that's the extragalactic interesting area. From that point on, the metrics scale with the amount of area that matches these criteria. And it also scales with the number of visits, but more specifically, it scales with the footprint definition, because one of the things about this traditional footprint is that we don't go further north than 0.2 degrees, and we don't go further south than -62 degrees for most of this part of the footprint. We don't go deep enough outside that area. And so the amount of area that they could possibly have in this footprint is limited. If you change the survey strategy footprint so that you go further north and further south, then this particular area that meets their criteria can be larger. And then that improves the metrics. The weak lensing metric is one that we've pulled out, and that's just the mean number of visits per pointing over that area. And then there's a 3x2 figure of merit emulator, a simple version. I believe they also have finished up a more complex version, but this estimates an approximate quality of the 3x2 cosmology constraints using the area and the depth. So this is kind of a combination of how much area did that meet those criteria, and then what was the depth over that area. So then we look at the number of stars. So we look at the stellar luminosity function and co-added M5 depths. How many stars can we detect? And in this, you can say, because the stars are very concentrated towards the galactic plane, you can say, what is the effect of crowding in the plane? And we probably don't have our crowding correction right just yet. That's something that is in progress still. But obviously the number of stars you detect depends on how you correct for the crowding, but mostly it depends on what your footprint definition was. If you include more sky that's near the galactic plane, you have more stars. If you don't, you have less. So it depends on the footprint definition, the area, and then the number of visits, because again, the luminosity function is shallow enough that as you increase the number of visits, your depth doesn't increase as fast as you can increase your area if you just boost the area. So here we have again the traditional baseline footprint on the left and a potential new footprint on the right. And you can see that there's more stars. If you sum up the number of stars across the sky, there's more stars on the right. So then, another of our core science pillars is the solar system. So here what we do is we just look at a couple of completeness points for the solar system objects. So what we do here, because the solar system objects move, is a little bit more complicated. We take a small body population, we simulate the observations of that population, which uses the individual image and 5 depths and the pointing locations. And then we simulate the linking requirements, so getting 2 observations per night for 3 nights. And so we say then what fraction of the population should we be able to discover as a function of size? So there's a bunch of different populations and they all have slightly different requirements, but you can kind of try to get the edges of this whole question by looking at large near-Earth objects. And this, the completeness of these objects here. So sorry, on the right here, we have a little plot. This is the cumulative completeness as a function of H magnitude. H magnitude you can think of as the size of the object. So for each of this is the NEO population. For the large NEO objects, the area is the primary driver for the completeness. How much sky did you cover? And that's because they're distributed widely across the sky. And as these are the big objects, they're fairly bright and you see them quite a fair bit. You have some other populations that we're not using as diagnostics for the radar plot, but that we do look at when we go more in depth for solar system completeness, for example. So the main belt, the Jovian Trojans, the main belt asteroids, and, oh, sorry, I had that backwards. This is, of course, the NEOs over here. So then you have the large NEOs for the area, the small near-Earth objects. So the completeness at this point in the curve, because they're smaller and they're fainter, this depends a lot on the number of visits and the cadence, because we're more likely to miss the objects if we don't have enough visits. And they're only visible for a shorter amount of time because they're smaller. And that makes sense because as they're smaller, they come closer to us, they get brighter, but that is for a much more limited amount of time. Over here is where we have the large trans-Neptunian objects. And because these are distributed over a much more limited amount of sky, the primary driver here is the footprint definition. In particular, if we don't get the northern ecliptic spur, the completeness for these objects drops by over 30%. After the footprint definition, the area number of visits and footprint definition, things like the filter choice is important. The solar system objects refer redder filters. The cadence is obviously always important. What seems to happen in looking at all of the simulations from my point of view is that there's sort of a threshold number of visits you need, and that varies by size. So for the big objects, because they're visible for longer, they're easier to see, the number of visits you need is not as many as you need to see a smaller object, which might be harder to see as you go. So then for transient detection, transient variables cover a wide amount of science. We include a few more transient and variable science metrics when we look at the particular distribution of all of the metrics for these. Like again, when we go in depth for TBS science, we look at more metrics. But these are some that we've pulled out to sort of this more overview level because they depend very sensitively on some particular aspects of the survey strategy, but also because these are sort of some of the most fleshed out metrics that we have so far. This is totally an area where we're looking to expand. So here we have a few that are sort of a little bit like canaries or so. So the tidal disruption events, TDEs, they're distributed all across the sky. So you can see a metric up here, whether we detected it or not. The timescales for these events is about 100 days. But what's really important is the filter choices and the number of visits for the cadence. And in particular, for detecting the TDEs and understanding that we saw a TDE in each U-band. So this metric is really sensitive to reducing the number of U-band visits or changing the cadence of U-band visits. Another area we have is the fast microlensing. So these are distributed near the galactic plane, so they become very sensitive to footprint. The timescales are much faster, about 100 days. So this depends very sensitively on the footprint, but also on the number of visits because they're much faster. We do also have a slow microlensing metric, but it was not as sensitive to the cadence. So that's one reason why at this level we've pulled up the fast microlensing, but not the slow microlensing. It's because it's sensitive to slightly different things in different ways. Now, Supernova 1A, this is actually primarily a cosmology metric because it is being driven by the desk group, or they're contributing this metric. But it is also a transient event. So I just put this here, but you could also say it was back in the transient or the cosmology section. Here, the timescales are longer, about 100 days. The cadence is interesting because it's being driven a little bit less by just when the U-band visits are, but it needs consistent coverage in all filters in order to be able to get a detect that it's a supernova 1A and also detect that it's what the characteristics are. And so this is interesting because as you learned yesterday, we have these basis functions that tend to prefer bluer filters when the moon is new and redder filters when the moon is full. And that makes sense because that's the more efficient way of surveying the sky. However, when you say, actually, I want consistent coverage in all filters across the month, that's actually pushing back on that. So because then you want bluer filters when the moon is full. So this is one thing that's kind of interesting here. Also, it depends on the area on the sky. So missing metrics. Like I said, there are a lot of metrics that we haven't talked about today because we don't have very long. But if you saw your metric or something that scales like your metric up to above, that's good, right? Other metrics we sort of think we're missing is a photo Z metric. So this would be sensitive to the filter distribution and the co-added depths. And we know this is in progress and it's coming soon. We would also love to see an AGM metric for structure function because this is dependent not only on the cadence within a season, but the cadence between seasons. And we also know this one's in progress. But yeah, we need to work with that team a little bit more, I think. Another one, we would like to see the weak lensing metric, but something which is sensitive to the seeing signal to noise and or camera rotation, because we don't really have a lot of metrics that are directly related to seeing, and certainly not the camera rotation yet. Transients and variables that are dependent on intra-night visits, so the triplets of visits. We don't really have metrics that are aimed at, or that show the benefit of having triplets of visits within a night. And I know that there's some in progress with the TBS group, but we need to talk to them a bit more about that. Metrics that are sensitive to period recovery for variables with realistic templates. So we do have some metrics that look at period recovery for simple sinusoidal periods, but nothing that's like with an RLI relay curve, for example. It looks like we should probably have some metrics that are sensitive to timescales that are on the sort of 50-day time scale for variability, maybe, or longer. See, we have that 10 days with the galactic plane distribution. We have 100 days or so with uniform across the sky, but there's phase space in between there that we're not including. Metrics related to determining the galactic structure in the halo, disk, and bulge. So this is I expect very sensitive to footprint, and this would be beneficial to have some more metrics. And deep drilling field specific metrics. So here there's a lot of overlap with our standard metrics, but are there other specific requirements to doing synergy with other data sets and so on? Metrics related to processing, classifying of follow-up requirements with the alert stream. This may be a little out of scope, but it may be a bit of a bit hard, but it's something to think about if we want to have some metrics that are sort of more specifically targeted to, okay, what do you do with the time series that you get? And metrics that are especially sensitive to the benefits of a short exposure survey, which I have heard is in progress. So we'll see that. That short exposure survey being the sort of 1 or 5 second visits. Okay, so yeah, this might be a good spot to take some questions because I have a little bit more of an example next. So
there was a question on Slack from Michael Strauss. Are there metrics that address science opportunities in the first year of the survey?
Not yet. That's a really good question. Mikhail, so as far as the solar system metrics go, I see there is sort of 2 questions there. There are more metrics for the solar system. There's not one on the orbital accuracy, but there are some about characterization. The solar system collaboration have said that looking at their roadmap, they believe that completeness is the very first and highest priority. There's a talk I gave to the Solar System Science Collaboration a week or so ago, which talks about the other metrics that we have. So I'll add a pointer to that in the Slack, unless Mike gets there first. But I don't want to go into that much more right here. They do exist, not the specific ones that I think you're talking about. Let's see, there were some in Zoom. Okay, yeah. So I admit that might be something to talk about more in split off groups, because it's talking about like how do we deal with crowding and so on. Okay, so one of the hard things has been once you have all these metrics, so it can be challenging to come up with a metric, but once you have a metric in hand, it can be a little challenging then to say, okay, what does this mean in terms of the survey strategy evaluation? So here I wanted to go through, so I talked about with each of these metrics, how they scale. And you might be saying, how do you know how they scale then? Because like, are you just making it up? And when I said that those are how they scale, that's based on how we see them behave with the different simulations that we have. So how do I know if it scales with the number of visits in the wide fast deep? We have a family of visits that looked at varying the number of visits in the wide fast deep. And this is the family that is called either wide fast deep depth or wide fast deep scale. Wide fast deep depth is the actual name of the family. I think in some places I might have referred to it as wide fast deep scaling because it's more maybe descriptive of like we scaled up the number of visits. But so basically you have these family of simulations. You can take your metric results from each of those simulations and you can see as the number of visits in the wide fast deep increased, did my metric performance improve? To look at the footprint simulate and whether it's sensitive to the footprint, we have a footprint family and we have a bulges family. These two kind of together make a easier way to look at like how did our metric change as a function of footprint. There's a filtered dist family. So this has a different footprint than the standard baseline. So you should consider, when you're using this family, compare it within the family. But what happens here is we change the filter balance in the wide, fast, deep between blue, red area, et cetera. And so you can look at, does my metric care about the filter, the distribution of visits between different filters? The intra-night cadence, we have a series of simulations where there's pairs in the same filter or a different filter, and then whether we took triplets in the night and how much time we spent on those triplets. So you can look at how did my metric change as the intra-night cadence changed. And then we have some families that were more specifically targeted at the effects of adding mini surveys. So there was a Twilight NEO family, a DCR family where we added high air mass, long season, basically, visits, a short exposure family where we added short exposure mini surveys across the sky. So if your science is benefited by these specific mini surveys, these are crucial to evaluate and see that they actually boosted your science. If you don't think they should benefit your science, they're still useful to evaluate because sometimes those visits are taking away time from the main survey. So the short exposure survey, if a 1 or 5 second exposure is not useful for your science, it's still taking up time on the telescope. So you would want to see how much is that survey changing the performance of my metric. So here are a little bit more examples. Here I'm using the radar plot because, like I said, all the metrics that we had relate to the radar plot. And we've shown these in, for example, the report that we had to the SEOC. However, so as you look at the radar plot, what you see is these different core science areas. So this is the solar system metrics, here's number of stars, number of galaxies, fast microlensing, the 3x2 figure merit relensing, the TDEs, the supernova, the FOMV, proper motion parallax. And it's pretty messy to read this many surveys, simulations on this kind of plot, but you can kind of get an idea like, oh, there was something going on here where fast microlensing was pretty happy, because further out is a larger number, and larger numbers are better for how we scale these metrics. If you, this on the right is a sort of zoom in of that same plot on the left. But you can also plot these in a slightly different way. Like I was saying, we have other plots where we take all of the metrics or a larger sample of metrics and just plot them linearly left to right. So radar plot, actually, I think this is really, really nice if you've got just a few surveys because it's clean. You can see, oh, did the area get bigger or larger? Where did it hurt? This is maybe a little bit easier for looking at some of these, especially when you have a family that trends left to right. So left is 65% of the time was spent on wide, fast, deep. To the right, it was 99% of the time. And then the very last value is the baseline. So you can see the SRD metrics are pretty linearly increasing as you increase the number of visits in the wide, fast, deep. The black line here is FOMV, which is the median number of visits over 18,000 square degrees. So it's pretty, makes a lot of sense that as you increase the weight, the number of visits in the wide, fast, deep, this metric goes up. Skipping down, so this is, for example, a series of number of visits per filter across the sky and so on. I'm sorry, I should have done a better job zooming into this plot when I put it in here, but hopefully it is visible. This is, all of these are also in the report to the SEOC. So down here we get to where I put in the TVS metrics. And again, I put the supernova metrics in this group, partly because there was already quite a few in the desk wide, fast, deep, but also these desk wide, fast, deep metrics up here are based on static science. So they might trend a little bit differently. You can argue with me about that, that's fine. I'm not committed to that anyway. But here we have the TVS. So some of these, you can see that there is, in here we do put in like, how well did we do at detecting or being able to see that there was a variability at a period of 5 days, 0.5 days. We also have the fast microlensing, the TDEs, those supernova, and here I did put in the number of stars, including a crowding correction in RMY. So you can see that for a lot of these, it doesn't necessarily change a lot, but for the TDE metric, or sorry, for the fast microlensing metric, it changed a lot. So when the Wi-Fast deep scale was very low, the number of visits in the Wi-Fast deep was very low, this metric was much higher than when you had a lot of visits that were dedicated to the Wi-Fast deep, which makes sense because those visits that are not in the Wi-Fast deep are going other places, including the galactic plane. Sorry, I did do a better job. Sorry, I'm so sorry, I forgot. So there's the SRD metrics as a scale. There's the desk Wi-Fast deep metrics, which also tend to scale with number of visits in Wi-Fast deep. And then the TVS metrics, which, as I was saying, they don't because of the fact that when you have more visits in the Wi-Fast deep, you have less visits elsewhere. And then the solar system is kind of a mixed bag here. More visits is good, but putting those visits in the rest of the sky is better. And so this tends to go down a little bit as you go to more, to a heavier rate on the Wi-Fast deep. Okay, then we have the footprints. Again, there's a lot of simulations, so it can be a little bit hard to see what's going on with the radar plot. So we can look at these more detailed metric plots. What I've done here is actually color-coded. So these are sort of the traditional footprint family. These are a family where we had no coverage at all in the galactic plane. And then these are a family where we had a bigger shifted Wi-Fast deep. So it's like extended north and south, so there's more extragalactic area. But then we started adding in more coverage like in the plane. Some of these have fairly heavy coverage all over the sky. And the story you can see here in the SRD metrics is that as you make the area bigger, because these tend to have about 19,000 square degrees or a bit more amount of area that gets a large amount of visits, because we've taken visits not just in the Wi-Fast deep, but also in the plane, also on this, the plane on this side and so on. And so the number of visits per pointing drops. So the SRD metrics drop. In some cases, we spent too many visits outside the Wi-Fast deep and they dropped too far. This line is sort of the lower cutoff. The desk Wi-Fast deep metrics, however, improve. Even though you have less visits per pointing, the footprint is more suitable for the extragalactic science because we're increasing the amount of area that's in that low dust extinction region. The mean visits per pointing for weak lensing drops because we do have fewer visits per pointing. Again, this is a metric that probably needs to include seeing and maybe some other aspects, but this is very nice. And then for the footprint, for the TVS and desk, sort of the transient family of metrics, you can see here with the fast microlensing the effect of anytime we include fairly heavy coverage in the galactic plane. So these have more coverage in the galactic plane, some more than others. This is a simulation with a traditional footprint where we just carried through the galactic plane in a smooth way. And these are simulations where we didn't cover the galactic plane at all. So you can see that these are terrible. So we can't skip the galactic plane. But maybe this new footprint where we have worse SRD metrics, but so far all the science metrics are improving is interesting. And then here we have the same thing for the solar system. The solar system is generally, the number of visits per pointing isn't dropping below thresholds. It's kind of maybe a little bit noticeable here where we're having fewer visits per pointing. But in general, the bigger footprint is an improvement in all of the solar system metrics. It's worth noting that these solar system metrics do not include crowding. So these, this improvement in completeness for the TNOs is, I suspect is coming from extra coverage in the north as well, but anything that's coming from extra coverage in the plane is maybe a little bit suspect. So that we may have some improvement to do on this, but it's hard to know exactly how to correct for the crowding and difference imaging. So these are some survey strategy questions that we are looking at and that we have yet to figure out the answer and optimize, for example. So the intra-night visits, should we do pairs in the same filter or different filters or triplets? Now it's worth noting that the visit time must remain 2 by 15 seconds until the on-sky performance of those snaps is evaluated. And part of that is going to come from what is the impact of satellites, unfortunately. We could vary the exposure time within some constraints. So for example, for U-band, and this is something that we are creating some more simulations to have a look at. What should be the distribution of visits between filters? And what should be the survey footprint? So here we have the WIFAS deep and big mini surveys, so the galactic plane coverage, northern ecliptic spur, northern coverage, and south celestial pole. Really, they work together to define the overall survey footprint, is what I have seen from looking at the simulations we've done, because you can't, these big mini surveys are big enough that they do interact with the WIFAS deep, and plus if we redefine what the WIFAS deep is, then that affects these big mini surveys as well. So understanding what the whole survey footprint should look like and deciding this is an important question. And it does have a trade with the number of visits per pointing in order to preserve for science. Then we have the time sampling from year to year in a rolling cadence, and possibly within a season. The deep drilling field survey strategy. This is primarily cadence. And these are deep drilling fields which are aimed at extragalactic science. I think that when you have a different deep drilling field, like there were some deep drilling fields that were suggested for things like solar system science or covering the Magellanic Clouds. And these are, I think they're a little bit different. We have in our heads deep drilling fields and their cadence, and in a way that is like sort of a unit of things that are for they're observed in a way that is suitable for extragalactic science, and the fields are oriented that way. And the amount of time to do the other suggested deep drilling fields is for the solar system or Magellanic Clouds, for example, is so much smaller that I think it might be easier for in order to like talk about this in a more clear way by talking about those as mini surveys or pencil beam surveys for the solar system, for example. And then we have other small mini surveys and what their strategy should be. So, sorry, that was the end. I meant to close with those questions. I didn't mean to click that one more time. But that is, these are the survey strategy questions that we still have to answer. And I'll have a little bit more to say about this in the next session when I go through like what progress have we been able to make on answering some of the questions that were posed from the COSAP, the Observing Strategy Community white paper. And so I think we have some ideas on this, but none of these are closed questions yet in terms of like being decided by the SCOC. So I think this is a good spot to go and check for questions. Let's see. When thinking about, so Meg had a question, when thinking about the rolling cadence, are there statistics metrics looking at the on and off bands to look at number of visits per year? And as Peter said, we have some metrics that look at, we've had some issues. I wonder if what Meg is asking here is basically, we've had some issues making sure that our rolling cadences are rolling as strongly and quite exactly how we wanted them to be, which is why there's a 1.7 release of rolling cadence. We've always made sure that they were rolling, but we have now done a better job at making sure that they're rolling at the level that we actually wanted. So yes, we have those metrics. And yes, in general, what we do is look at sort of metrics that are, when we're evaluating the rolling cadence simulations as a whole, what we do is look at the science outputs of those metrics.
And can I interrupt? Because my question's slightly different.
Oh, okay.
It's that there was a raised question that was raised of the parts that are off, right? They're not the one you're rolling on, focusing on. The people that study comets want to know that they will be able to find their thing that just went off, or their, their PHA. And so it was, how do you know how many visits that off-roll thing is getting to evaluate whether that works, since detections might not necessarily tell you that, oh, it only came back like twice that year. Which I know you're like, none of them should be that extreme, but I was wondering if you have plots or something that, because it seems like without having to do any fancy solar system simulations, right, that would probably be enough to tell you whether you'd be happy with that if you were a comet person.
So, you know what? We, as Peter said, we can, but we typically don't. But this is actually a good reason to do that and include that in some of our outputs. So yeah, we have, like I said, we have a lot of metrics that are the metadata style metrics, like just, hey, how many visits across the sky did you get? What was the seeing distribution, air mass distribution? This is a good one that we can put in there as well. Another metric that people tend to see is the Hourglass Metric, which is showing like what filter you're looking at what time over the survey. So yeah, so this is totally the kind of metric we can put in that metadata area, and we will do that. That sounds like a good plan, especially because it's actually helpful now. And then need to include the TO family. So, okay, we simulated TOs in one of the early releases. What we found was that we were essentially, because we were basically making up the TOs, and they probably did not represent a realistic selection. Or maybe they did, but nobody ever, we couldn't find it. We couldn't determine if we were doing the TOs realistically. And so basically what the TOs were, the impact of the TOs was just as if they cut off a few percent of the survey time, and that percent would be entirely determined by the SEOC or whoever says, okay, TOs can have 1%, 2%, whichever, the survey time. And so since we didn't know that answer, and we didn't know how to program like the trigger requirements, for example, are you going to follow TOs anywhere on the sky, or only within the Wi-Fi deep footprint, only when that part of the sky is already like suitable to be observed? We decided that we weren't going to add more of those simulations right now because it was not clear what information we were getting with that, with those simulations. So if there's a good driver for going back and following up on the TOs and seeing, especially if there's a change in something like what the triggers should be or so on, that would be, we can simulate those again.
Lynn, can I make a comment about something that you just said? You said, obviously the TO time is outside of the Wi-Fi steep, it's outside of all the surveys. So yes, there's going to be like an upper limit, which is what is the percentage of time that can be allocated to this. But I don't see how the SEOC or whoever would be able to make a decision about what that fraction of time is without knowing the throughput of following these TOs. So I think that understanding, obviously I agree, it's very difficult. It's a baby field that just started, so it's obviously not clear what the TOs will look like and what is the best strategy to follow them up. But if we don't simulate them, if we don't have a metric about that, then I don't see how we can say this is the percentage that will be allocated, because if there is no throughput, even a small percentage is wasted.
Yeah.
But if
It was also not clear how to evaluate the output.
Right. So, but I think it should really be together with the other metrics that are missing, perhaps with like star, this is particularly hard to actually do at this stage of the field, but it can't be omitted from what is actually missing.
Okay. I think this is worth talking about more, maybe not right here, but let's talk about it more. One of the problems was that we, in order to evaluate like whether the TOO was successful or not, it's yeah, I mean, we can tell you these were the visits we took for the TOO, but we don't know. I think it's hard for us to say like, yeah, that would have been a successful follow-up without knowing more about like what the brightness of the thing we were trying to follow up and so on, what the light curve might have looked like. I'm not exactly sure what else we would need, but let's talk about it. And yes, we can add those back in. One of the things we were hoping for example, with the understanding a little bit better about the constraints on the triggers, was if the triggers were going to be something like in Wi-Fi steep only, within certain amount of, within certain number of days of the center of the season, then maybe it does start, it's not completely off the top of the survey, but again, that's really hard for us to know at this point. So it may be safest to just say, it is this % of time, we don't know how much it is. And then if you're saying, okay, what we need is a metric to evaluate whether the TOO was successful or not, then we need to work on that. And we don't know exactly how to do that right now. So
I would like just to add one thing. This is Ross speaking. So in our white paper that we submitted, we went through the troubles to lay out 2 potential strategies, an ideal one and a minimal one. And we do have a metrics for success. We do lay that out. That is based on our ignorance right now of how these counterparts might look like, but you do have that information. And I would be very happy to work together and see if we can, if we can understand exactly what is the input of TOs, what is a success given our current knowledge and ignorance.
okay, yeah, that would be good. We did, yeah. That would be good. I think that RTO simulation built on the strategy that was suggested there, but maybe was not exactly the same in the end. So we can come back and have a look at that, sure. You think?
Lynn, is this your last slide or?
Yeah, this is my last slide. Sorry, this is why I was just going through questions. When was the breakout time? It's like.
We have to go through Peter's slides and then.
Oh shit! Sorry. Yes.
Gather town and then we have break.
Yes, I'm so sorry. I will. I believe that the other thing is that all the other questions are stuff we can deal with offline.
Thank you so much. As I hope everyone can see, this is extremely complicated, complex problem to decide what is an optimal strategy for us to do. So we really do need your help. We only have 2 people working on this, and they have other things they work on, not just on this. So it will be extremely important to get science collaborations and individuals to help us. And if you wonder how can you acquire these ninja skills to go through simulations and produce all these amazingly beautiful and informative plots, this is the topic of the next talk. Peter will show you what, in collaboration with Data Lab people in Tucson at NOAA Lab, what they set up for you to use and make it much easier on you than if you had to install all the software. And this is like 21st century analysis framework. You basically log in, data is somewhere else, you don't even know where it is, but you run your Jupyter notebook and you do analysis just like you had everything on your laptop, but you're doing it over the internet from any place where you want to be. So that's the main purpose for Peter's talk, in addition to a few other details. So let's go to Peter's talk, and then we'll again have a little bit of discussion, and then we'll see how much time we have for Gather Town before the break. So Peter, please take it over.
Okay, let me give a quick introduction to the metrics analysis framework. Okay, there we go. Okay, so we go and simulate 2 million observations with Rubin Observatory, and we're asking the scientific community, how well can you do science with these 2 million observations? This output, if you go look at the databases, it's basically all the relevant information you'd expect from your typical logbook or like the FITS headers. So we're not giving you pixel data, but we're giving you the metadata. So the RA deck, time that things happened, how long it was, the filter, the air mass, the sun altitude. We've got 41 total columns, and they're in the repo if you want to see all the data there. But it's kind of all the things you would typically expect information about an exposure. And so we have things like this. So here's the co-added depth in R band for our baseline and then combo dust. And you can see they look pretty similar, but there are some significant differences. And we want to ask the question, which one's better? And then we'll, of course, follow that up with, well, how much better? And then finally, can you show your work and give it to us so that when we run new simulations, we can answer this ourselves again. And so some of the questions are easy. For example, you can see on the baseline, there's very little coverage of the LMC and SMC, and here there's a lot. So people who want to do LMC, SMC science will say, well, this one's clearly better, but we still want to know how much better. And you can see there's bulge coverage differences, and this one has rolling cadences. So light curves will be very differently sampled. So we really want to know how well you can do science in these two cases and compare. So there are three components to any MAF analysis. The first is there's a SQL query where you do a SQL query on the database. Usually this is a filter, maybe a time period, or just empty quotes. You just grab all the information. This is pretty much the most common, filter that. Next up, there's a slicer, which defines where on the sky you're going to look. And finally, a metric is what you compute at each slice point. So let me just go through here for co-added depth. The SQL command is give me the R-band filter. The slicer is a heel pix slicer. We use heel pixels, the centers of heel pixels as a grid on the sky to analyze the co-added depth. And we have a co-added depth metric. The co-added depth metric, the code looks like this. And so this can be expanded to compute whatever you want. But basically, the important thing is, whoop, wrong button, come back. There we go. The important thing is this line down here where I'm saying, take my data slice, that's all the observations that overlap at a point on the sky, and give me the 5 sigma depth, and then do the whole magnitude things of convert it to flux, sum it, convert it back to magnitudes, and return it. And that gives me the co-added depth at that point. And this will run at every one of the heel pixels. So, and obviously you can put much more code in here if you want to do a more complicated analysis at the point. So that's how we generate this map. The slicer finds everything that overlaps with a given heel pixel at its center. For display purposes, we're coloring the whole pixel. So this is a good approximation if we run at high resolution, maybe not great at low resolution. So both MAF and the scheduler are using a grid of points as reference, not contiguous area. So that can be important if you want to speed up your metric and run at low resolution, you might get confused. By default, MAF assumes all the points within the science field of view get observed. Technically, there are chip gaps, and they're the wavefront sensors in the corners. So these corner chips don't count as science. So that's not included in MAF. But also sometimes you can see there's silicon outside the science field of view. So sometimes you get extra observations. For the most part, that should even out, but you can't expect things to be off at kind of the 1% level because we're not fully taking into account the chip gaps. You can turn on the focal plane geometry, but it just makes things really, really slow. So that's why we're doing this approximation. All right, so that was looking at a grid across the whole sky. The other common way to run MAF is to define a population of objects and only look at those points. And so for example, here is our fast microlensing metric. And so what we do is we distribute fast microlensing events based on stellar density. So this is a map of our input events. And we give each of those points a start time and light curve properties. And now when we run math, we just go to each of those light curve points, and the metric code generates each light curve and tests the detection criteria. And now we say, 0 or 1, did we successfully detect that microlensing event? We can flip back and forth, and you can kind of see, you can see those couple points out there disappeared. We didn't pick those up, but some of the other ones we did. And obviously, most of the events are concentrated on the bulge, and so that's where we detect most of them. I like them. You can see the LMC and SMC pop in down there. So some tips for math. If you're not using the 5 sigma depth of each visit in your science metric, you're probably doing it wrong. Basically, we have a lot of observations taken in a wide variety of conditions. Because Rubin Observatory is a single instrument facility, we're taking observations in twilight, we're taking observations in bright time. Sometimes we have experiments where we mix in 1 or 5 second exposures, and those are all included in that list of 2 million. So, and there's no good way with the SQL query to say, just give me good observations. You really need to do a filter in your metric code to say, put in a 5 sigma depth limit or include that. So usually when you're writing your own metric, you want to compute the signal to noise ratio of some fiducial object. So you might say, so for example, for our parallax and proper motion, we say, I'm going to pretend there is an R equals 20 star at every heel pixel on the sky, and I'm going to see what signal to noise I get on my proper motion for that star. Or you could turn it around and compute the faintest object you can reach, your desired signal to noise to. So you could say like, oh, I reach quasars to 25th magnitude here or 26th magnitude there. And you don't need to select, only wide, fast, deep observations. There's no such thing as a wide, fast, deep only observation. So just run on the full sky. Running on the full sky is a great way to test your science metrics, because for the most part, just about all of them should do really well in the deep drilling fields, and almost all of them should do poorly on the edges where there are just a handful of visits. And so it's a really easy way to check that your metric is behaving and scaling properly, because we have such a variety of observation depths across the sky. Okay, so if you want to do this, please, everyone, don't log in at once. There are like 100 people logged in here, and we would denial of service attack data labs if we all logged in. So save this link for later in the week. There are instructions on if you want to install MAF locally. However, you can run it in the cloud at datalab.noao.edu. They have installed our software stack, and we have lots of the output databases available there. It works. If you log in, you get a Jupyter Lab interface, and you can click on LSST Sims MAF, and that will bring up a Jupyter notebook that has all the MAF tools ready to go and available, and you can connect to databases and so on. All right, so conclusion, MAF is up. If you want to start developing your own metrics, we want your metrics, and I'll just emphasize, talk to us early. We've written lots of metrics at this point, and the most useful ones tend to be the ones where we work in collaboration. It's really hard for us to write science metrics on our own, and we found science collaborations struggle with the simulations if they try to tackle it on their own. So working together, we've made lots of good metrics, and we're looking forward to more. That's it. Any questions?
Thank you, Peter. If you have technical questions, again, please type them in Slack. So I see some comments. Radar plots are confusing. Okay, already advanced that. Will had a question about 5 sigma depth.
What is the current status of the? We have some metrics that include crowding, but it'd probably be good if people double check those. And says, yeah, so when I say 5 sigma depth, that's the 5 sigma limiting depth for a point source, and it's computed from the sky brightness, air mass, and image quality.
And we can add the extinction, add extragalactic dust extinction to get sort of an extragalactic M5 value. But yeah, calculating the M5 depth just in the galaxy, but including spatial confusion, has been tricky. And I think at the moment we're waiting for some help from experts. Is that right?
It'd probably be good to have a double checkup from the experts that the metric we have is in fact.
As in, we did calculate the number of stars we would expect, and then it didn't. There's some discrepancies between what we calculated and what some surveys are reporting, but some of that might have to do with the pipeline that the reporting is using. So it's really hard to know exactly what we should put down for that. And we need feedback from people who are maybe more expert in that area.
Thanks.
I'd like to add a comment that when one develops a metric for a specific science case, it's very easy to go down the rabbit hole and produce something that may be justifiable from the science point of view, but in this context becomes essentially noise. We do not care about effects that are 0.1 or 1% even. What we are here is to see changes at the 10% level. So if I now develop some new methods that can improve, let's say, finding periods of RL-Lyrae, and I show I can get 0.1% more RL-Lyrae, maybe that's interesting for something, but definitely not in this context. So we should, if you have so many metrics that you run out of resources to implement them, then I would rank them by how useful they would be in distinguishing different cadence strategies. We've done similar errors in past where we had some metrics that were not very useful at all. But again, communications is going to improve greatly whatever we do and you do and how efficient it will be and useful to us. So to remind you, we do have community.lsst forum where you can ask all the detailed questions, and that's where all the discussion, technical discussion is taking place. So let's try to record all these discussions as we now expect many more people to join this effort. I'm very excited that we have over 100 people participating in this workshop. My initial guess was that maybe 30 people would show up. So I'm very excited that we have so much interest. And so let's work together over the next 3 months and push this to the next level. So if there are, let me double check. So it looks like we don't have any direct questions right now. So we could now switch to Gather Town, and then we would be back on Zoom by 11. And when we go to Gather Town, there are basically 4 topics that we want to address. And depending on people's science, they may be interested more in one than the other. So the first topic that will be led by, discussion will be led by Lynn, is about footprint definitions and the assignments of visit counts per footprint. Then the second group that I will lead discussion will focus on optimal exposure time. So why is it 30 seconds and why we would go to 15 U-band and why we have 50 something visits per U-band or 180 for R and I. Where do these numbers come from? And do we want to revisit them and re-optimize them? And then the third topical group will have discussion led by Peter, and they'll talk about temporal sampling strategies with emphasis on rolling cadence and how could you implement different flavors of rolling cadence idea. And the fourth group will be discussing deep drilling field strategies. As you may remember, the white papers, the 8 white papers that we used to design strategies for deep drilling fields were submitted in 2011, almost a decade ago. So we want to revisit that. And so this fourth group will focus on DDF strategies. It would be great if there are any actionable items from these discussions to post them back to Slack. And that's basically reminder to Peter, Lynn, myself, and I believe Colin, if I remember correctly, Colin or Dan Skolnick, I forget now who was assigned for DDF, but it would be great to have some written feedback. And then let's reconvene here on Zoom at 11 Pacific. Thanks all, and see you in Gather Town.
Yeah, and one note on Gather Town. So for the later breakouts, there's a number written in the carpet in the breakout rooms in the corners. So 1 is the desk area, 2 is TVS, 3 is solar system, and 4 is galaxies, I think.
But we have different topics now. How shall we? Can we use these numbers to go in the order of our topical discussions right now?
So can you remind the first one, are we not going to science collaborations?
Number 1, no, this is now focused on open questions. So let's do number 1 is footprint. Number 2 is optimal exposure time. Number 3 is temporal sampling. And number 4 is DDF. Same order as on the agenda webpage.
Yeah, sounds good.
Thanks.